Hello, this is Nicholas from Silicon Chip Magazine, and I just wanted to have a relatively quick run through the current issue, which is the August 2025 edition of Silicon Chip Magazine. This is the cover, and then we can move on to the contents here. I'm not going to talk about every single article in detail, but I'll quickly go through what's in there, and then I'll go through 7 articles in some level of detail. So we have a feature on SpaceX. This is the second half because it was too long to fit in one magazine. Talks about the Starship rocket and then some other things. Then we have a educational article on amplifier cooling, basically how to design or modify audio amplifiers or other high power gear to keep them cool even in difficult situations. And then we have a short article on a thin film pressure sensor. Basically, what are they? What are they good for? How do you use them? That sort of thing. We have a review of this Rigol DHO924S oscilloscope, which is a very nice looking, relatively inexpensive but very capable oscilloscope. It's also quite compact. We have an article on the Boeing 737 MAX. Of course, there have been a lot of articles about Boeing's aircraft in the last year or so, but this is more of a technical look at what the angle of attack sensor is and how it works and why it can go wrong, that sort of thing. And then we have our constructional project articles. There's a USB-C power monitor. So this is an update of a project we did quite a while ago, measuring current drawn by a USB device, power consumed, that sort of thing. Now it's been updated for USB-C, so it can handle current flow in both directions. It can handle higher voltages, higher currents, that sort of thing. We have this development board based on a Raspberry Pi chip. It's kind of like a Raspberry Pi Pico, but more powerful with more pins, and it can be overclocked. It has quite a few nice capabilities, a fair bit of memory. And then we have a fun project, Mick the Mouse, which is a little mouse that you can build and hide, and it will make squeaking noises. And if you make too much noise, it will be quiet. So it can be difficult to find because if you're too loud when you're looking for it, it will just be quiet. And then later on, it will start squeaking again. And finally, we have the ducted heat transfer controller, which is something you can build into a home. So the idea is if you have a heater or air conditioner in one room and you want it to heat or cool other rooms, this will automatically transfer air through ducts between those rooms. It has quite a few different modes to handle different situations. So now I'm going to look at the first article in detail. And this is the article on cooling amplifiers. This is by Julian Edgar, and he talks about both amplifiers he's built and also ones he's modified. So here's one he's made. In fact, I think he might have made both of these. This one uses the aluminium case as its heatsink, and it also has a fan. A lot of what he talks about is using fans, usually low-speed, quiet fans, to assist in the cooling of amplifiers, which in many cases are designed to be passively cooled, but that may not be adequate depending on ambient temperature and how hard you're driving in them and things like that. And you can't just stick a fan anywhere because it won't necessarily do much. So a lot of it is about, you can see in this example here, he's cut a hole in the lid. I believe this was a metal lid he's replaced with plastic, cut a hole in it for the fan, and he's also made holes along here, and you can see they correspond to these heat sinks. So what's going to happen is if this fan is exhausting air out, it's going to suck air in through these holes and then across the heatsink, across the board, and then out here. So it's a pretty effective way to cool an amplifier. And he goes into quite a bit of detail. And here's another example. This is a tunnel heatsink, which is something we've used before, and I particularly like because when you have a tunnel heatsink, the air has to pass through it. It can't detour around it, and it's going to be flowing pretty smoothly. So it's quite an effective way of transferring heat out of the amplifier. And the other thing is, in this case, you can see he has a push-pull arrangement. So this fan sucks air in, goes through the tunnel, cooling it down, and this fan pushes it out, and it's going to go straight out of the case, so it can't circulate and heat things up. So more examples. And he includes talking about thermal cameras and things like that, how you can actually tell whether it's effective and what the hottest parts are. So quite a useful little educational article there. And there's a second part. So this part mainly talks about the theory and what to consider when you're building an amplifier, and the second part talks about what to do if you have an existing amplifier that's running too hot. How do you modify it to run cooler? So now we can move on to our second article, This is the USB-C power monitor, and you can see here it's quite a neat board, and we've used a trick that Tim has used a few times now, where the front panel is one side of a circuit board and all the circuitry, or almost all of it, is on the back. So you have a single board that acts as both the panel and the circuit board. You can see how he's got the screen here that shows through a cutout in the board, and similarly these buttons stick through holes in the board. The charging light shines through a hole in the solder mask there. It's a clever arrangement. And this shows here how it's actually made of two boards. One board is basically just a plug and a socket that passes the USB signal and power through, and then this other board monitors the voltages and currents and does the calculations, shows the result on the screen, and there's a battery in between that powers the whole thing, which is handy because while you can power things from USB, you don't always want to. For a start, if this is powered off USB, then that's going to add to the load, and you're not necessarily going to get accurate measurements. So by having it powered by a battery, you remove that from the equation. Here's a list of the parts you need. Here's the circuit, and you can see how it's split into two boards. This board here has the sockets and some resistors, and then it connects by the flexible cable to the main board. Here we have an instrumentation amplifier and an op amp with some passive components feeding into the microcontroller. So that's for all the monitoring. That's for monitoring the voltage and current, calculating power and energy. It has this OLED screen, which is an I2C communications, and that's what shows the results, your buttons, and then the rest up here is a power supply, which is includes a battery charger, the battery, and a switch mode regulator to provide the regulated 5 volts to run everything else. There's the secondary board with the resistors and the connectors on it. That's pretty much it. Again, there's a second part, has the information on actually building it, testing it, setting it up, that sort of thing, because it doesn't all fit in one part. Moving on to the next project, now we have this development board that I mentioned. It uses the RP2350B processor, whereas the Pico 2 uses the RP2350A, and the difference is the number of pins. So this has 80 pins instead of 64, so you get 16 more pins, which means you get more I/O pins, and that means this module is bigger, but it's more capable. It's still breadboard compatible, but it has 7 or 8 analog capable pins, which is more than the Pico. Yeah, in fact, you can see the 8 pins here are sort of the yellow on black. And it just has more IOs in general, and many of which are capable of PWM, serial, I2C, and SPI. Some of its other features, it has linear regulators, which are less efficient than on the Pico, but they are much more stable, which means you get better analog performance for things like measuring voltages or audio, and importantly, it's better for overclocking because you get a more stable core supply. And this trim pot here lets you adjust the core supply. So if you're going to be overclocking the chip, you can set up the voltage to be just what you need for stability. Here's the flash chip, which I believe is higher in capacity than what's on a regular Pico 2. It has 16 megabytes of flash instead of, I think, 4. And it has the built-in 520K of RAM that comes on these Raspberry Pi chips, but it's expandable to over 8 megabytes by adding an optional PS RAM. It's called pseudo SRAM. It's actually a DRAM chip, but it has internal refresh, and the interface just looks like an SRAM to the microcontroller. Other than that, it's pretty similar. I think another difference is it uses an oscillator module rather than a crystal for the clock, and that just improves stability. So here we have the circuit, pretty straightforward. A lot of it is just the RP2350B chip connected to headers, but of course we have the RAM and flash. We have the oscillator, the power supply with the USB socket, and so on, and also USB communications. And of course we're using USB-C because that's the standard now. Here are the parts you need, but you don't really need to buy the parts because we sell the module as a pre-assembled unit. The only soldering that you need to do is add the headers, and if you want to, add the SRAM chip. Here's an example of what you can do. You can drive this display with parallel I/O because there are plenty of pins, and there's still many free pins even doing that. And this here shows you how you can adjust the DVDD core supply. I think from memory, I can't remember if it's 1.1 or 1.2 volts is standard, possibly 1.1. But if you're going to clock it higher than the standard clock rate, then you would use a higher VDD. I think it's safe up to about 1.4. Beyond that, well, here it's what it says, a maximum 1.4 is safe. You can push it higher if you really want to overclock it, and yes, it confirms that the default is 1.1. So a very capable little development board, not too much more expensive than a Pico 2, but quite a bit more powerful. We sell the assembled board for 30 Australian dollars, and subscribers to the magazine get a 10% discount. That doesn't include postage, but obviously if you bought more boards, well, we charge a flat rate of postage, so it's a per order, not per board. And then now we should move on to the next article. And this is the Regal oscilloscope review. One of the important features of this oscilloscope has 12 bits of analog resolution. It used to be that 8 bits was the standard. For many years, that's really all you could get unless you spent a lot of money on a scope. Now this is an entry-level scope that has 12 bits, which I think is really nice. If you're doing work with something like audio, it really gives you the precision that you need to see the details of a signal. And it also it starts with 125 megahertz of bandwidth, which is pretty nice for an entry-level scope. 4 channels, again, very nice. You used to get 2, and you'd have to pay a lot to get 4. So overall, it's just a really capable, nice looking oscilloscope. We were given a demo unit to test, and we give our impressions of it. It was lent to us by Amoni Instruments, and they sell this scope for under $1,500 Australian, which personally I think is very good value. If I was looking to buy a scope, I would seriously consider this. And they also have a multimeter that's in the same case. Nicely, they've made it a different color plastic, so you can tell straight away which one is which. And again, it looks like a very capable unit. If you need a bench meter to go with your scope, it looks like a very nice accompanying unit. Moving on to the next article, we have Mick the Mouse. A very simple circuit here. You can see there's a microcontroller, there's a MEMS microphone module, so all this circuitry here is on the module that's pre-built. Not expensive, a few dollars. And then basically the microphone feeds sounds into the chip, and the chip decides whether to make squeaking noises with the piezo, flashes the LED eye. It runs off a 3-volt coin cell, and there's not much more to it. It's just a power switch diode, so that if you put the cell in backwards, it doesn't destroy anything, other than possibly the cell, but that's the cheapest and easiest part to replace. Here are some scope grabs showing how the piezo is driven, a view of the circuitry on the back of the board, and it's just a fun little project that you can use to play pranks on your brother or sister or parents or something like that, who might think there's a mouse in the house when there isn't really. Next article is the ducted heat transfer controller. So you can see here a pictorial representation of what it does. So if you have a fireplace in your lounge room and you want to keep the bedrooms warm, it will automatically turn on a fan when appropriate to pull the warm air from that room and push it into the other rooms. And it's very configurable. You can see here that it has options for how much the temperature has to differ before it switches the fan on, from between 1 and 11 degrees Celsius. Hysteresis, which determines how much the temperature has to change before it will switch off, which you can also set. Timer options, so you can either just have it decide itself when to run the fan, or you can turn it on and then have it run for a certain period before it turns off. This is the sort of kit you can buy that includes the fan and the ducts and the vents. And our controller is designed just simply to control that fan. List of all the parts that you need. Here's the circuit, and it shows the main part of the circuit, which is the microcontroller switching some relays to control the fan, with some BCD switches for settings, or if you want to save a bit of money, you can leave the switches out and just use jumpers. Given that it's pretty much going to be set and forget, the jumper option is not a bad option. And then we have these RJ45 sockets, so you can use Cat5 or Cat6 cables to connect temperature sensors. You'll need at least 2, obviously, at each end of the duct for it to determine when to switch the fan on. And then also this control panel, again connected by a Cat5 or Cat6 cable, that lets you see what the unit's doing and manually switch it on or off. So that's a pretty straightforward design, a neat circuit board here that fits in this box and does all the work. And then we have some tables showing you the different modes and settings. And then finally we come to, now Circuit Notebook usually has a few circuits. There's 3 this month. I'm just going to talk about this one because I think it's particularly interesting. And it shows you here, where you can see some scope grabs as well, that how when you're driving it, this is the normal way to drive an optocoupler, which is an optocoupler is a way to electrically isolate things. So you have a driven end and a driving end, and so they're not electrically connected. They're connected by light. So here, if you're just driving the LED to turn on the phototransistor, the problem that you have is it will switch on very quickly, but it switches off very slowly if it's been driven into saturation. And that means you can't send signals very fast through this cheap optocoupler. However, what you can do is, and this is what I think is very clever, you reverse the phototransistor. So you're actually using it more like a photodiode. And by stacking two optocouplers, because with a photodiode, it's almost like a miniature solar cell. So basically, when the input is driving the light through the LED, that energy will actually induce a voltage across the transistor. You only get about 0.3 of a volt, but if you stack, or 0.4, but if you stack two of these, that doubles the voltage, which is enough for you to switch on a transistor. This does not have the saturation problem that the standard configuration does, so you get much more bandwidth through the optocoupler. Even though you need two, it's still a lot cheaper than buying a high-speed optocoupler. And here it shows if instead of having two, you can just use the one, and then you can use a high-speed comparator to sense the voltage that's developed across the transistor, so you don't need to double your optocoupler. So I think that's a very clever little circuit snippet that in itself doesn't really do anything, but could be very useful if you're designing a circuit and you need to isolate a high-speed digital signal. So that's most of certainly not all of what's in Silicon Chip magazine. It's 104 pages, most of which is content. So you can see from the contents page here, we also have an article on the Silvertone AM/FM radio from, I think it was 1954, based on valves. Quite an interesting article if you like old radios. We have Serviceman's Log, which has some stories about people fixing things and what went wrong and what went right, that sort of thing. Of course, the SpaceX article I didn't look at, but we also have that. A thin film pressure sensor. And then a few little bits and pieces. We also have some letters from our readers and some questions that they ask and we respond. So I think quite an interesting article of the magazine. It's a monthly magazine. You can subscribe to a printed edition or the online version. And if you subscribe for 12 months, you'll get 12 issues, and each issue has different content, but along these lines, usually about between 3 and 5 feature articles, 4 constructional project articles, typically, maybe 5. And then all these extra, the letters, circuit notebook, Serviceman's Log. There's always a vintage radio or some sort of a vintage equipment article. Ask Silicon Chip, where we answer questions. And then a few other bits and pieces. So I hope you found this interesting. In a couple of weeks, I'll look in detail at another article like I've been doing for the last couple of months. But we'll also, most months, we'll take an overview look at the whole magazine, the new magazine. Okay, thank you very much.